My name is Aadi Kenchammana, and I did my project on fighting fires with AI. So just kind of a brief introduction. I think everyone's familiar with wildfires and how big of a threat they kind of pose to us. And just as like an example, in 2020 alone, they caused over $16 billion in damage to insured property and over $93 billion in damage due to reduced economic productivity. And in that same year, they caused over 10.2 million acres of land to be burned during the course of about 58,000 different fires. And so during wildfires, the only tool that firefighters have are these things called fire breaks. And these are just natural or man-made obstacles to control the fire spread. And while they're very effective, they're also very time-consuming and expensive to build. And they're difficult to effectively place during an unfolding crisis. So I propose to use a field of machine learning called reinforcement learning to build a model that optimally places fire breaks in a developing wildfire. This model will be coupled with an upgraded wildfire simulator, and I will evaluate my combined method against actual wildfire responses. So just kind of briefly going into my methods. This is a rough visualization of the algorithmic workflow. So the agent, which is kind of like a virtual wildfire fighter, will make a decision about which action to take, either up, down, left, or right. That action will be passed into the custom environment, which uses the simulator to simulate out the wildfire for one tick. The custom environment will return two parameters back to the agent. First, it'll return the state space, which is kind of like a representation of what's happening in the environment. And it'll return a reward, which critiques the agent's previous action. And based on if the reward was good or bad, the agent will update its decision-making policy and then kind of repeat the cycle. It'll go on and on until the training is finished, at which point a policy will be outputted. And this policy is the mitigation placement. So going a bit more into the placement algorithm, it does not actually place fire breaks itself. Instead, it trains RL agents to generate these fire breaks. And it'll evaluate both policy gradient, PPO, and Q-learning, DQN based agents, which are just two types of models in reinforcement learning. And to give a bit of context, Q-learning or DQN has been primarily used in previous research, but I believe that PPO could outperform that. And so to give you an idea of what a general RL training workflow is, you'll take the state space, which is like a visualization of the environment, and you'll pass that observation into the agent. In my case, this is a neural network. The agent will make an action, which will be critiqued by the reward function. And based on this critique, the agent will be updated. Its weights will be updated using a technique called backpropagation. And to go a bit deeper, so as I mentioned, state space is how the agent kind of sees its environment. And in my case, this is with a grid with two channels. The first channel is the fire state, which is, whether squares are burning or burnt or unburnt or mitigated. And the second channel is the burn risk, which is whether or not a unburnt square will ignite soon. And so as you can see on the left side, these are some visualizations of what those layers kind of look like. The action space, which are all the possible actions the agent can take, up, down, left, right. And the reward function, which, as I said, critiques those actions, is this. And I landed on this after testing many other reward functions because this performed the best. Anyway, to dig a bit more into my simulator, as you can see, my simulator takes in three major data sources. The first data source is from Landfire, where it pulls fuel and topography data. And there's Wind Ninja, where it gets wind direction and speed data. And finally, there's Modus. And Modus, I actually get satellite data from, which I then pass through a previously published temporal CNN to roughly estimate the fuel moisture content in that area. These three values are passed into my simulator, which uses the rothermal fire standard for the industry in fire models. It uses that to generate the fire spread grid. Anyway, that's the methods. So let's look a bit more into the results. So here are the results of training both DQN, the red, and PPO, green agents using my framework. And so this specifically, this metric is the end of episode reward, which is just what the reward function is at the end of an episode. And an episode is basically one complete simulated fire from start to finish. And basically a higher reward just indicates a better performance, a better containment. And so as you can see, especially in this blue square, PPO, which is in green, in this blue square, PPO consistently outperforms DQN. And just to kind of explain these big drop-offs that you see, every about 2,500 episodes, I change around the fire parameters. So the agent is not too specifically trained on one instance of a fire. This is a generalized training. And here's like an example of what the mitigations that were generated in this training cycle kind of look like. So as you can see, not only did PPO significantly reduce the burnt area by over a factor of 4, additionally, it successfully mitigated and contained the fire. So even if this was still alight, it could not spread. On the other hand, DQN left large sections unmitigated and prone to fire advancement. So as I mentioned before, I wanted to evaluate my system against an actual firefighter response. So I chose the 2020 Slink wildfire. And so what I did is I took the generalized PPO agent, whose training I showed in that previous slide, and I fine-tuned it over 10,000 episodes on the Slink wildfire. And what fine-tuning is instead of changing around the parameters as I did every 2,500 episodes, I kept all of the parameters, including the fire ignition position, completely constant, so the agent would have the chance to generate the best mitigation strategy it could. And so to give you an idea, this is a rough visualization of what the actual Slink fire would have looked like. And this is what it would have looked like if with my generated placement. And so as you can see, my agent was able to achieve a burnt area reduction of about 1,100 acres, which is about 4.15% of the total fire spread area. Additionally, this solution only took about 2.5 hours to generate, which is significantly less than the 4.5 hours it took to train the generalized PPO model. Anyway, this is a kind of demo of what it looks like to generate the mitigations. I think the biggest thing you should take away is that my agent does not simply place all the mitigations at one time. Instead, it progresses through the environment like an actual firefighter would, moving from one space to another. And so as you can see, it kind of wraps around the fire and goes up, preventing the fire from spreading anymore. So beyond this point, it doesn't spread anymore and the fire is effectively mitigated. Anyway, to draw some quick conclusions, I think my research has absolutely demonstrated that reinforcement learning can be successfully applied to contain wildfires. And if implemented, my system has the potential to significantly reduce the area burnt by wildfires. And research is never done. So I have some future work that I would like to address, namely leveraging novel machine learning-based techniques to predict the fire spread, which could outperform the thermal fire model that I use. And additionally, improving the placement algorithm by allowing it to use multiple agents, allowing it to have more realistic travel and construction times on heterogeneous terrain, and specifically to have protection of privileged regions like residential or developed areas. And this would just help it better emulate the activities of real wildfire fighters.
Great. Thank you so much.
Yeah.
Question here that's about your data, and if there's any other data sources that you think, you mentioned the data sources that you were using to develop the model. Are there any other data sources that like you wish you had or that you think would help you improve the model as you move forward?
Absolutely. So the source that we pulled I pulled my wind data from, which was called Wind Ninja, it's not actual wind data. Instead, it is a wind simulator. It's a very accurate wind simulator, but it's still a simulator. And I tried using NASA satellites to actually predict what the real wind was in that area, but it proved too difficult because the granularity of wind data that existed was not fine enough both spatially and temporally for me to use for this application. But in the future, I'd absolutely like to explore that a bit further.
Great. Thank you so much.
Yeah, thank you.